Welcome to this session on analog and digital signals. Hopefully by the end of this session you will be able to understand the joke on the t-shirt. There are only 10 types of people in this world, those who understand binary and those that don't. Okay, so by the end of this session you'll understand that joke. First of all, I'm going to explain the difference between analog and digital signals. So, analog is data represented by continuously variable, measurable physical quantities. Okay, so it could be the change in pressure, it could be the change in volume or frequency. So these are constantly changing values. Digital is data represented as a series of discrete numerical values. So it doesn't show constant change, it shows a series of clear numerical values. I think this is best shown graphically. So the analog signal, we see there's a constant change, a continuous change. Whilst the digital signal here, we have clear different values. And these values don't constantly change, they just jump from one value to another change. There's not that gradual change we see with the analog signal. So let's just look at some examples of either analog or digital. I'm going to show you some diagrams here. Okay. So first of all, in the top left we have an analog voltmeter. It shows the continuous change, whilst top right we have a digital voltmeter. What we have here is digital because it will go from 2.52 to 2.53, and there's no continuous change there, so they're clear discrete values. My speedometer here is analog because it shows a continuous change, and also my how much fuel gauge I have is another example of an analog measuring device. Okay, so those digital devices which we are quite aware of, they control or they collect data in a digital manner. A digital manner often means using something known as a binary system or a binary code. So I'm going to explain what this really means, and actually it's a way of counting for computers to understand. So let's think about binary numbers to start with. Okay. First of all, I've got binary numbers from 0 to 15. Binary means there's two options. Okay. So on each of these examples I've used the fact that we have 0, 0, 0, 0. So that equals 0. No numbers have been counted. Next value I've got is 0, 0, 0, 1. That equals 1. Now this all makes sense so far. We've got 0 and then 1. The problem is when you've only got two numbers, you don't have the number 2 available to you. So what you have to do is then say, okay, that means that I've got now 0, 0, 1, 0. That 1, 0 indicates that I have 1, 2, and then a 0. So 2 plus 0 equals 2. 3 in turn is going to be my 0, 0, 1, 1. So that first one equals to 1 and the second one equals to 2. Let me show it in a table which is kind of more informative. Okay. So I've got some random numbers here, and what you can see is that any number, the number gets bigger, the number of digits used gets longer and longer and longer, but what we're really doing is we're adding up features. Okay. So my first binary number is going to be 0 or 1. Okay. My secondary binary number represents the number 2. So here it's either going to be, there's going to be 2 or there's going to be 1, which means I need the number 2. My next binary number looks at the number 4. Okay, so in that case I have either number 4, it's going to be 1, 0, 0 equals the number 4. And what I'm really doing here is adding up these different numbers in these different locations to tell me what my final number is. I've got some examples here up on the screen. So 60 is going to be 4 plus 8 plus 16 plus 32, and that equals 60. So I can work out that that is 60. 66, on the other hand, is interesting because it's just 1, 2, and then 1, 64. Now, these 64, 128, these are factors of 2. Okay, so they're all going to be factors of 2. So for 1, it's going to be 2 to the power of 0. For 2, it's 2 to the power of 1. 4, it's 2 to the power of 2. For 8, it's 2 to the power of 3. So I can recognize that these are the key factors I need to know in a binary system. You're going to spend a lot of time practicing this. It's not too complicated. With a little bit of practice, this makes perfect. Now, binary numbers are very, very, very useful. Now, the IB says we need to be able to solve conversion numbers between binary numbers and decimal numbers. That's one thing you need to do. You should also be aware of these two terms, the least significant bit and the most significant bit. Okay. And problems will also be limited to a maximum of 5 bits in a digital number. So let's look at this here. The binary representative of the decimal 149 with the least significant bit highlighted. So just think about what 149 is going to look like. 149 is going to be 1, 0, 0, 1, 0, 1, 0, 1. Okay. Now that 1 there is the least significant bit. Okay. So it's the part of the decimal which has represents the smallest number. Now, if I do the binary representation of 149, and this time I'm going to highlight the most significant bit. So the most significant bit in an 8-bit binary number represents the value of 128 decimal. So that means it's the largest number which is shown in a binary number. So there's the most significant bit and the least significant bit. Some terms to get used to here, bits and bytes. A 1 or a 0 is a bit. Okay, so every single 1 or 0 here is a bit. Now a byte is a string of 1s and 0s. We've got the example above, and this is an 8-bit byte, and see how it's BYTE. Now it can represent as many as 256 different numbers. Okay. So remember, that's 2 to the 8, so that's 256 numbers. And all the 8 bits set to 1 plus the 0, so that's 256. That's 1, 1, 1, 1, 1, 1, 1, 1. Will give us 256. So that's an 8-bit byte. And if we have 16 bits, that gives us 2 bytes. So that's what we remember here. A byte is made up of 8 bits. I guess a little note here that if we think about kilobytes and megabytes, they're thought of slightly differently to how we would normally do. So in the decimal system, the prefix kilo means 1000. But in the binary system, the prefix kilo means 1024. The reason for that is a 1024 is 2 to the 10th power, or the maximum numbers that can be represented by 10 bits. Thus, 10 ones in a row can be represented by the decimal number 1023 plus the value they're all set to 0. That means there's 1024 different numbers available to you. So just remember, this is kind of a computer system here, and therefore 640 kilobytes of memory is really 640 times 1024 bytes in total, which makes 655,360 bytes in total. The final thing I want to talk about is digital sampling. So this is the conversion from analog to digital. What we have here is when we take some sampling, the amplitude is sampled at a given time interval. So at every specific time interval, what they do is they provide a number. so it's rounded to a nearest integer value, and this is ADC, analog to digital converter. All these integers are converted into binary numbers. In this case we've got a system where this is a 3-bit example, but it can be more complicated if needs be. This data can be sent and then it can be decoded, and that can be decoded with a digital to analog converter, and that means that each one of those numbers is then transferred, and what they really do is they join the dots. Okay, so it's a little less subtle there, but for each of the values they join the dots. Now that dot joining is, I guess, the reason why some people will say, well, it's maintained, it's actually true, that the detail in an analog signal is contains much more information. This is true, and therefore people often say that sound recorded on analog equipment has got much more depth to it, but the advantage of digital equipment is that this digital data can be transferred very easily, even though there's not quite as much detail in it. So that's the idea of binary systems and analog and digital data. I hope this helps.